In 1915, Einstein published the field equations of general relativity. The theory had been sought due to a need to understand the effects of gravitational forces on external observers, and indeed its prediction of various cosmological observations, such as the precession of the perihelion of Mercury, or the bending of light, were a proof of its success. But the theory held other results waiting to be discovered. The equations show that space and time are intrinsically intertwined, forming the spacetime, and in turn that matter and spacetime are coupled together. This strict relation challenged our understanding of gravity. The presence of a mass influences the environment around it through the way it warps spacetime, and this distortion then dictates how other masses move. One particular prediction of the theory revolutionized our notion of the influence possible by gravity, this being that of the existence of black holes, bodies so massive and yet so small that no information can escape from within, hence the name. Such entities are impossible to detect directly since their strong gravitational field is able to bend spacetime such that light passing in its immediate vicinity is pulled towards them. However, light farther away is focused the same as it would be had it passed through a lens. This optical effect serves then as an indispensable clue to their presence. Black holes' influence is such that the more massive ones at the center of galaxies can bind planets thousands of light years away. No other celestial body is known to exert such a far-reaching and powerful force. But how are black holes created? Stars burn their mass as fuel in fusion reactions, producing heavier elements and increasing their density. It is predicted by the field equations that, should a star be massive enough at the end of its lifetime, then its own gravitational pull will force its contraction against all internal pressures present. The whole mass of the star will thus collapse on its center, forming a singularity. During this process, as the surface of the star passes its corresponding Schwarzschild radius, all information becomes trapped inside, unable to escape. It is then the black hole makes itself apparent to any external observer. After the collapse, the process ceases, and the black hole becomes stationary. The intensity of the forces involved makes this process extremely violent, and consequently any falling object approaching the singularity is completely destroyed and stripped of its details. As such, a black hole is wholly defined by its mass, charge, and angular momentum. The black holes can thus only be distinguished by those characteristics and have no other feature, or as it is said, black holes have no hair. But there is more to the process of gravitational collapse. As the star converges over its singularity, the strength of the field on the vicinity of the center achieves its highest strength. Its effect on spacetime and matter forces the conclusion of the process in an ordered fashion, which proves to be similar to that verified for other black holes of the same type. It is at this point the identity of the black hole through its characteristics is set. Because these phenomena have an analogy with those found in the phase transitions of more common matter, like that between ice and water, they have been called critical phenomena. It follows then that the study of these critical phenomena is key to a better understanding of how the gravitational collapse of a star defines the resulting black hole and how spacetime itself is affected during the process, and in particular at the point of convergence.